So my name is Austin Brand, recording on September 23rd, 2025. And today we'll be looking at ketamine. Ketamine was discovered in the 1930s as a replacement for PCP as an antidepressant and analgesic. In the 70s, the FDA then approved it for medical use. And currently it's mostly used in the veterinary field, however, still also in the medical field for humans as an antidepressant and analgesic. It's a controlled substance, so it can cause addiction and is abused in some circumstances, but in a controlled environment can be very useful. So, ketamine here, IUPAC name 2,2-chlorophenyl 2-methylamino cyclohexane 1-one. All right, we have our three functional groups on the left, and I will circle the amino starting now. Amino. Second is our chlorinated phenyl group, right here. And then lastly, our carbonyl, right here. Okay. Right in the middle is our chiral carbon. This is our chiral center. So it has four different functional groups. The one that you don't see is a hydrogen, which I will draw now. And the hydrogen. Okay. So starting with priority, first we're going to have the amino group because nitrogen has an atomic number of 7. And then moving side to side, we have 2 carbons. So the tiebreaker would be connection to the following connected atom. So the carbonyl is going to be attached, double bonded to an oxygen, giving it second priority. And then the chlorinated phenyl will have third priority. All right. There are 2 enantiomers of ketamine. All right, we have our S-ketamine, which is commonly known as S-ketamine, so ES-ketamine. I know, very creative. And then the other enantiomer is going to be R-ketamine. Typically, a racemic mixture of both is used, but S-ketamine is found to be more potent, and R-ketamine is found to be less potent. However, it has less psychotomimetic effects, meaning induces less delirious kind of hallucination side effects. So there's debate on whether just S-ketamine should be used or the racemic mixture, but there's a lot of research going back and forth. Now they are enantiomers because in the middle, we'll draw a mirror plane of symmetry. These are non-superimposable images. And then I will also draw hydrogen for both, for the chiral carbons. So you see hydrogen here, on the other side hydrogen here. And in order to find the stereochemistry, we'll have to pretend like we're looking directly at the hydrogen. So our eyeball will be somewhere over here in the back, looking towards it. And as we know, the amino has the most priority, then the carbonyl, then the chlorinated phenyl. So here, if we're looking into the page, this will be going to our left, this will be going to our right, and the carbonyl is at the bottom. So it would kind of be like this. And counterclockwise, S. Whereas on the other side, we'll have to be looking into this hydrogen as well, meaning the amino will be kind of to our right, chlorinated phenyl to our left, and the carbonyl at the bottom, giving us the opposite orientation, the R orientation, because it goes clockwise to the right. All right.